So today we are going to talk about the semantics of first-order logic. If you recall, last lecture was all about the syntax of first-order logic, also known as predicate calculus. Right, so we can draw out this table. Right? We have syntax and semantics. And last lecture we talked about what it means to be a well-formed formula in first-order logic. And today we're going to talk about what it means for a well-formed formula to be either true or false. So before we get into that, I just wanted to note that today should be fairly easy. If you were to graph maybe the difficulty of this course over time, it would look something like that. And we're probably about there right now. So making things nice and easy for you, comfortable going into the midterm. But we are going to be building up from here again, working on these concepts and making them hard for you to get to the final. So, but I'll also make sure to post the notes from today on Learn, so you don't have to bother too much about copying down examples and stuff. Just focus on trying to understand what the definitions are, because there's going to be a lot that's kind of being thrown at you and they'll build upon themselves. So it might seem fairly innocuous and straightforward at first, but these things will get difficult if you can't sort out one definition from another. Okay, so with that said, we will recall from last lecture. So we defined what it means to have a language in a first-order logic. And this was done by breaking down the symbols into two parts. There were the logical symbols that are independent of any... Oh, I forgot the light. There we go. So we have the logical symbols that are independent of any particular language. And those include things like brackets, our connectives, right? So that's like these guys, and then our brackets. Then we've also got quantifiers, and lastly, we have the special symbol for equals. So these are the things that are going to exist in all of the different first-order languages that we look at. And then the things that are dependent on the particular language that we're choosing, so the language-dependent symbols, are going to be the things that actually have some connection to the semantics of the language. So these are things like constants, which we'll typically list out as C1, C2, and there could be infinitely many. Oh, sorry, I also forgot one other thing here. We also have variables. And we list those as x1, x2, and you can have infinitely many variables. So we have constants, and then we also have functions. And we typically denote these as lowercase letters like F and G, or with subscripts F1, F2. And then lastly, we have relations. And we typically denote these by uppercase letters like R, T, P, stuff like that. And both the functions and the relations can take some finite number of parameters. It could be 1, could be 2, up to any finite number. So far, all of this is purely syntactical. We saw some examples from last class that kind of highlighted some examples of how you can see this is connected to semantics, but we never actually went through and defined how you go about saying what's true and what's false in this language. So we're going to work towards that bit by bit today. So first off, again, recall what it meant to be a well-formed formula. I'm gonna kind of go through this quicker than you did last lecture, but it's important to restate because, again, the definitions build upon each other. So we have a number of definitions. We had what were the terms. So you can think of the terms as basically what you can get by inductively combining all of your constants and variables together with your functions. So we're not yet looking at relations, just constants, functions, and variables. And you can recursively apply these things together as many times as you want. And intuitively, what this is giving you is like all of the different values that the language can represent. And it could be composed of constants, which are fixed, or variables, which can be like injected later on. So we'll talk about that in a bit. But if we want to be a bit rigorous about what it means to be a term, we can define this as the set IAP, where our core elements are going to be our constants and our variables. And then our operations are going to be given by our functions. And this is kind of an abusive notation because these aren't strictly operations, but it should be clear what it means when I talk about the function in the context of an operation. So we saw some examples last class of what it would be to be a term. In the language of number theory, a possible term might be something like 3x plus y or 7, something like that. But again, this is not syntactic. This is more semantic because we don't have access to the number 3 or the number 7. These are these in themselves too are also terms. So if we wanted to actually represent that syntactically, what we'd be doing is something like G, F, 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 B, B. I think I got an extra F there. X. Right, so you can see how this is kind of annoying. We like to think of things in these terms rather than these terms. But today what we're going to do is show how you can get to things like that. So those are our terms, which in the context of the language of number theory can be thought of as all of the polynomials over a set of variables. And in general, that's what that is. We've also got atomic formulas. And atomic formulas are going to be the simplest possible formulas that are legal, well-formed formulas. So terms are not well-formed because like 3x plus y doesn't have any like truth associated with it, right? It's just some other value in our domain. But atomic formulas are going to be the simplest things that can be given a true or false value. And they'll be defined as taking any number of possible terms that we can generate and combining them together with one of our possible relations. So formally, this is going to be Ri applied to some number of terms where Ri is a k-ary relation and Tj are terms. Okay, and it's important to note that among the possible relations that we can choose, this also includes the equals relation. So that's language independent, so it'll be one of the relations we can use. Okay? So an example of this in the language of number theory would be something like 3x is less than or equal to y. And that does have a truth value associated with it, depending on the values of x and y. Okay. Then lastly, we have our well-formed formulas. See if I can fit it in here. And basically, the well-formed formulas are going to be the same as they were in propositional logic, except now our core elements are going to be the set of atomic formulas, and the operations we can apply to these atomic formulas are going to be all of the same ones we've seen so far, our logical connectives, but then we're also going to have these quantifiers for all and their exist thrown in as well. So formally, that can be stated as IAP, where our core elements are atomic formulas. So these guys here. And then we can combine them together by any number of our connectives, as well as we've also got an operation for every single variable that we can potentially attach to a quantifier. So we have for all xi for any I. And we've also got there exists xi for any I. So that's kind of just, again, I'm kind of abusing notation a bit because these aren't technically operations, but it should be clear when I write this what it means for that to be applied to something inductively in IAP. Right, so it's basically the same thing that we've seen so far for propositional logic, except now our core elements are a lot more expressive, and we've also got these extra quantifiers. So now what we're going to do is move on to giving a definition that's somewhat analogous to truth assignments in first-order logic. So in predicate logic, we had these truth functions that could map from all of our different variables to some assignment of true or false values. And we're going to do something analogous to that here. But before we get to that point, what I first want to do is recall free variables, because that's going to be important. Right, so if we have like, let's say we're talking about the language for number theory again. So in the language for number theory, we had constants a and b, and those stood for 0 and 1 respectively. We also had the function f that was doing addition. We had g that was doing multiplication. And what else? We had r that was doing less than or equals. And what we'd like to be able to do is express things like what we might want to do is say, when is something like that going to be true? Well, b is 1, and x is going to be in the domain of natural numbers. So this is going to be true if and only if x is either a or b, right? So we're allowed to pick x, and it has to be less than or equal to 1, so it has to be either 0 or 1. So we'd like to be able to talk about the truth value of this, but you'll notice that we have a variable here that we don't know the value of, right? We don't know what x is going to be. And that's precisely what we talked about last class when we defined what it meant to be a free variable. So a free variable informally speaking, a free variable is just a variable that does not appear in the scope of any quantifier somewhere within the formula. So a free variable of phi is going to be some variable not in the scope of either one of our quantifiers somewhere in phi. So that's kind of a informal definition, right? But last class we actually gave a formal definition of it, and it was recursive. So you can refer to that if you so please. It's maybe more informative to just go through some examples. So maybe we have for all x rxy. So x appears in the scope of a quantifier, but y does not. So y is free. Now, what about if we take the same thing and maybe AND it together with something like p of x? What are the free variables going to be in this case? Yeah, so it's still y. And now if we do what I meant to do and change that to y, now what is the answer? So according to our definition, to be free, it just has to appear somewhere not in the scope. So it's still free. Okay, hold on. So those are the obvious examples. And then what I wrote before, I think. So in this case, what did I want to do again? Yeah. So, yeah. So in that case, what are the free variables going to be? Yeah, x and y. So it's kind of important to note because even though it appears in the scope of this quantifier, there's another place it appears that it's not in the scope of quantifier. So x is free in addition to y still being free. Is that okay? And again, intuitively, the free variables are telling us which ones kind of need values in order for us to like interpret what the formula actually means. Because we don't really need to know anything about x in this case, but we do need to know something about y in order to say whether that expression is going to be potentially true or false. And as one last example, say we have this. Now what are the free variables going to be? So this is actually a trick question because this is not a well-formed formula. Because f is one of our functions, so it maps our values onto another value somewhere in our domain. So this is kind of nonsensical, right? What does it mean for all x and y to have some value? And this goes back to our definition of well-formed formulas, right? We can only take things that are atomic. And atomic formulas always have to be some relation applied to our terms. In this case, we don't actually have a relation applied to our terms. If you were to change this to R, then it would be a valid formula, and z would be our free variable. Okay. One other thing worth noting is we have the following definition. If phi has no free variables, then we say that phi is a sentence. And sentences are kind of the more interesting formulas in a sense, because they're the ones that we can say things about without knowing anything about the contents of our variables. So for example, this would be something like for all x, for all y, are xy. Right? This is an example of a sentence because it has no free variables. And stuff like that is interesting because if this is true, then it's basically saying that our relation isn't like doing anything. It's always true no matter what for all x and y. So yeah, intuitively, our free variables are the ones that we need to assign values to. But before we get there, we have to be a bit more rigorous about what is the actual function of these different constituents in our formulas. So what are these relations doing and what are these functions doing? And we'll need some idea of that in order to actually define the truth value. So what we'll do is define something called a structure or an interpretation. And you can think of this as kind of like the semantics that we're endowing on all of the different relations and all of the different functions in the language that we fixed. So, right, we just fix some language that we're talking about, right? We fix our constants, our functions, our relations, but that's purely syntactical. In order to introduce semantics, we have to say, what are these relations actually doing? What are these functions actually doing? So we define something called a structure. So given some syntactical language, and what I mean by given some language, I mean given choice of constants, given choice of functions, and given relations. And these, again, are purely syntactical. These are just symbols that reside in our world. And we're given these symbols, and now what we want to do is define a structure. A structure, which is also sometimes referred to as an interpretation. It's because you're interpreting what these symbols actually mean. A structure consists of So a structure consists of a number of things. So the first is a universe U. So that's just a fancy German U, because why not? And a universe U is a collection of elements that reside in our domain. So you can also just call it a domain. And important is that our universe has to be non-empty. If we have an empty universe, bad things happen. The next thing we have to do to interpret these symbols is say what all of our constants mean. So we have to give an element in U to each constant. Okay? And technically, according to this, you can have two different elements in our universe, both with the same label. That's fine. Really, all the constants are doing are labeling particular elements in our domain that are special or that we're interested in. The next thing we have to do is say what all of our functions are doing. So the structure consists of a mapping for each function, and this function is going to map from elements in our universe to other elements, where fi is a k-dimensional function. It takes k arguments. Right, so in the number theory example, if we're looking at our addition function, k is 2. It maps two elements in our universe to some other element in our universe that is going to be the addition of those two elements. And similarly, each relation is going to have a mapping. And rather than mapping to some other element in our universe, the relationship, or the relation, is going to map to either true or false, depending on if the inputs satisfy that relation or don't satisfy that relation. And again, here, Ri takes k parameters. So this is enough to formally define everything we need to know about our language. Because now we know what all of our constants are doing, what all of our functions are doing, what all of our relations are doing, and what are all of the possible things that we can build up our formulas on. So if we go back to our example of the language of number theory, we can now be a bit more rigorous about this language. So just as an example, our constants, so we're talking about the number theory language. We've got constants A, B. We've got functions f and g. And we've got one relation. And these are just symbols, so they don't actually say anything about number theory yet. This is just our syntax. Now, to endow the language with semantics, we have to come up with a structure. So the structure for this language will be as follows. It should be pretty clear what our universe is going to be. Right? It should be the set of natural numbers. We've already said what A and B are. A is 0, B is 1. Then our functions are going to do what you would expect them to do. right? So we've just said what each of these symbols are effectively doing. So there should be nothing too surprising there. But we have to do this in order to actually be rigorous about what the truth value is going to be under this interpretation or under this structure, because the structure does actually matter. It will change the truth value of different formulas. So maybe we should do some examples of that to see. So it should be pretty clear from here how to go, at least when we don't have any free variables. So if we look at maybe some example sentences, so sentences are formulas that don't have free variables. Look at so we'll consider the following formula, and this is going to be in the language of number theory. So for all x, if x is not 1, then we're going to have that 2 times x is less than x squared. Right. So that's an example of our sentence because there are no variables that don't appear in the scope of any quantifier. And it should be fairly clear that this is going to be true in the language of number theory. Right, and why is that? Well, using our semantic interpretation of these symbols, we can think of this as saying for all x, if x is not 1, then 2x is less than or equal to x squared. And you can check that that's correct. If x is 0, 0 is less than or equal to 0 squared. If it's 2, 4 is less than or equal to 4. And then the rest is easy. Okay? So now what about the example, you take any x, y, and z, and now the claim is going to be that if x is less than y, and y is less than z, then it must be the case that x is less than z. Sorry, less than or equal. And again, it should be clear that this is true as well. This is the transitive property for natural numbers. Everyone sees why. But again, I was saying that the structure that we fix on our language is very important because you can easily imagine structures under which these two will no longer be true. Can anyone suggest maybe a modification to the language that would make one of these false? Yeah.
The first one is false already. That's the x equals to a. Oh, never mind. Sorry.
Yeah, if x is equal to a, 0 times 2. Yeah, so a is 0, so 0 is always less than or equal to 0 squared. But can anyone see a way that we can modify the structure here to make one of these examples false? Yeah.
Well, if the universe was not the natural numbers, like the real numbers, then the first one would not always be true, right?
Yes, that is correct. Because in the first example, we only had to specially handle the case where x is not 1. But if our domain is the real numbers, then there's a whole bunch of other numbers around 1 that are also not going to satisfy this. So we could imagine changing our universe. Can anyone see an example that doesn't involve changing the universe?
Make b equal to 0 and a equal to 1.
Yeah, that's an easy way to do it. Yeah. Yeah, so you could reinterpret the value of b, and then suddenly you're not checking if x is not equal to 1, you're checking if it's not equal to something else, and then it's going to be false. So this is just going to show you why it's important that we be clear about what the structure of our language is, and why there is this clear difference between semantics and syntax, and the fact that we have to fix our interpretation of what these symbols mean in order to actually understand what the formulas are saying. Okay? And one last example, maybe, what about this formula? Clearly, it's a well-formed formula, right? It's an atomic formula. What is the truth value of this formula? Well, the problem is we don't know, right? X is free, so it's going to depend not only on the structure that we fixed, but also on the assignment that we're making to the free variables. And this is where kind of the analogy of truth assignments come into first-order logic. So you can think of these sentences, the ones that don't have any free variables, as kind of the tautologies or the contradictions in our language. They're the things that are going to be true or false independently of any sort of assignment to the variables in our language. But as soon as we start introducing free variables, we have to ask ourselves what are the contents of those variables. And that's kind of like our truth assignment. But we do have to be a bit careful. Just because like sentences are either going to be tautologies or contradictions doesn't mean that they're the only tautologies and the only contradictions. There are also tautologies and contradictions that do have free variables. Can anyone see an example of that? As a clue, there's actually one on the board right now with a little modification. So we're looking for an example of something that's a tautology or a contradiction regardless of the fact that it has free variables. Yeah.
For the second one, can you just take out like for all y?
Yeah, exactly. You can take out any number of these quantifiers. In fact, you could take out all three. What you're left with applies for all x, y, and z. So clearly, it's a tautology. And that happens even though you have these free variables. So I'm just trying to make it clear that it's not as simple as just either being a sentence and being a tautology / contradiction and not being a sentence and then having to need a truth assignment. There is this kind of a gray area in between. And you can even take it a step further and notice that there are even contradictions and tautologies that don't even depend on the chosen structure. So we can actually just fix the syntax that we're talking about and then allow the semantic structure to be any arbitrary semantics that we can think of. And there are still even tautologies and contradictions in this setting. Can anyone think of one? Yeah.
X equals x.
X equals x, yeah, that seems like a simple one that would work.
It's not a
But,
well-formed formula.
so,
It's not atomic. Is it?
no, it's atomic.
Oh yeah, equals is allowed. Okay, yeah.
Yeah, so that's fine. I'm just trying to think of, I think we do have to be a bit careful because even though we listed equals under the language independent symbols, it still doesn't have any semantics up to that point. So we haven't actually said what it does, but yeah. So I'm going to make the argument, though, that if we have something like this, I'm going to make the argument that if we have something like this, it's going to be true no matter what semantic structure we pick, given that we have the right interpretation of what, actually, yeah, maybe I shouldn't make this argument for the same reason that I didn't accept your answer, because we do again have to be careful to understand what these symbols mean. So, okay, forget what I'm saying. You do have to pick a structure and be careful about how you interpret these symbols in order to say that that's a tautology. But the reason I brought this up is because it is an example of how to go from one quantifier to the other. So anytime you have a for all quantifier, it's the same thing as saying there doesn't exist an x where it doesn't hold, right? And it should be clear that this actually goes in both directions. So what this is kind of showing is that we've made our language more expressive than it actually needs to be. We could have easily dropped there exists, or we could have easily dropped for all, and our language could still do all the same things. It's kind of just there for convenience. It's the same thing as how we have all of these different connectives, but all we really need is those two to be adequate, right? Because them together can express any other connective. So from all of this together, you should be able to see that these three connectives, or these two connectives in this quantifier, are going to be adequate for first order logic. But we're not showing that today. This is kind of just a brief aside. Okay. So now, yeah, we showed what we can do in the case where we have sentences, but we have, yeah?
Just what was the P like in the previous example? It's just like
Oh, it's
some
just a relation that took one
some
argument.
relation, okay.
Yeah. But now what we want to do is we want to be able to say what the truth value is going to be, regardless of whether or not there are free variables. So what we're going to do is define a general mapping similar to what we did for truth assignments in propositional logic, and then extend that to handle any well-formed formula, regardless of if it has free variables or not has free variables. So hopefully this should look familiar to stuff we've done already, but it's a bit more complicated now that our language kind of has a couple layers. So the first thing we have to do is we kind of have to start from the bottom and say what are the simplest things in our language going to get. So to be clear, what we'll do is define an assignment function and this assignment function will take us from the set of possible variables to the elements in our domain. So these are our variables. And then these are the elements in our domain once we fixed our structure. So what this assignment function is doing is basically saying what all of our free variables are. If we don't know what x is, we look it up in this function, and out pops what it actually is, and then we can proceed to find out the truth value of our formula. So this is kind of analogous. This is kind of analogous to the truth function v in propositional logic, whereas v was saying that different propositional variables were true or false. This function is saying that our different variables, what they're going to be in our domain. And from that, we can then extend this to handle all well-formed formulas. But we have to continue going up from the bottom. So we have something that tells us how to handle our variables, but we need to be able to say how to handle terms, how to handle atomic formulas, and lastly, how to handle well-formed formulas. So what we'll do is, going from the bottom up, we'll extend S to S prime, or S bar, and S bar will take us from the set of possible terms, and these terms, again, are going to give us back elements in our universe. Because recall the definition of terms are the things that we can inductively build up from our constants, our variables, and our functions. So our functions are mapping things in our domain to other things in our domain. So the thing that we're going to get out of our S is still going to be something in our universe. So to do this extension, we have to do it inductively because our terms were defined inductively. So the base case we have some t, and t is a term. So what can it be in the base case? Either t is a constant, and in that case we just say that the value of t is the constant itself, or t is a variable, in which case we use the function that we've been given to get the value of that variable. Right? So if you think of like the case of the theory of natural, or the number theory language, it should be pretty clear what's going on here, right? So if we say that x is 5, and we're extending this x to be a part of a term, then it's still going to be 5. But if we encounter a constant such as 0 or such as 1 or a or b, we just plop in that value of whatever that constant was. So this is fairly trivial. In the inductive step, what we have now is that t can be written as some function applied to some number of terms, right? So we're doing kind of the standard structural induction on our IAP definition of what it means to be a term, and all we're doing is just saying how to define our S bar in all of these cases. So we know what S bar is for each of these subterms. Now we want to say what S bar is for t. It should be pretty clear that S bar of t is just going to be f applied to S bar of each of the parts. Right. So all we've done so far is taken our function that tells us what the value is for each one of our variables and extended it to be able to handle arbitrary terms. So for example, if we know that sx is 3 and sy is 4, then s bar of 2x plus y would be 10, right? And that's just done by induction. Yep. But now we can handle terms, but we want to be able to handle well-formed formulas. The next step is to be able to handle atomic formulas. And again, recall atomic formulas are taking any one of our relations and applying it to any combination of terms. So we want to extend S bar again to handle atomic formulas. So we have some atomic formula that we can write as maybe phi is going to be some relation applied to right. Phi is going to be some relation applied to a bunch of terms, right? That's just our definition of what it means to be an atomic formula. And in this case, S bar of phi is just going to be the relation applied to S bar on each one of the terms. And this is a bit subtle, but some of you might complain. Were you going to, yeah?
It's not returning something in the universe?
Exactly. So I'm kind of abusing notation here because I've gone from an S bar that returns stuff in our universe to an S bar that returns true or false. And I'm mainly just doing this because I'm lazy and don't want to keep coming up with new letters for things. Like we could just like call this like S hat or S tilde or something, but really I don't really see any purpose of doing that. We'll just keep reusing the same S bar, and it should be clear from the context what it's actually returning. So if it's taking an atomic formula, it should be clear that it's returning true or false. And if it's taking a term, it should be clear that it's returning something in our universe. Okay? The final step, and probably the most annoying step, is going to be extending S bar to handle any well-formed formula. So this is actually our base case, right? Because the atomic formulas are the core elements in the IAP for our well-formed formulas. So we're good there. Now what we need to do is handle the inductive step of building up these atomic formulas with all of our different connectives. So we're going to extend S bar one last time. To handle any well-formed formula phi. So what do we know about phi? Well, we know the operations that it's built up on. So again, we're just going to use structural induction and look at all of the cases. So the first few cases should be fairly obvious. Right, suppose phi can be written as not eta for some eta that we know the value of S bar for, then S bar of phi is going to be true if and only if S bar of eta is false. Right? It's the same thing we did for propositional logic. And similarly, we've got the other cases where we can write it as running out of letters. What's that letter again called?
Ada, I think you said? No.
This is eta, this is
Psi?
Psi, yes, thank you. Yeah. So we've got the same thing with all of our different connectives. And in each one of these cases, we just use the truth table for S bar of eta and S bar of psi. Right, so exactly the same thing that we've seen already for propositional logic. Where things start to get more tricky is when we have to handle these quantifiers. So the remaining two cases are when we can write phi as something that involves for all or something that involves there exists. So we'll just, without loss of generality, consider so we'll consider it of the form being quantified over xi. And the fact that I've written I here is important, right? So we have all of these different variables that we could be quantifying over. We're going to suppose it's being quantified over the given I. And now what we have to do is figure out what the truth value this is going to be given this truth value. And this is kind of where free variables come into play. But we won't explicitly invoke our definition of free variables. What we'll do is we'll basically modify the S bar to properly handle the case that xi is known when we're evaluating eta, right? Eta, yeah. So have you guys taken like a course where you write like any compilers yet, or do you still?
Unless you've taken CS245 L15.
Okay. Like, are you familiar with like dynamic scope and like stuff like that in Scheme, where you have to basically worry about like closures and stuff like that? So if you're familiar with that, that's kind of what we're doing here. We're kind of building a closure in a sense, because what we want to be able to do is say what the value of eta is going to be, but we know what xi is when we're evaluating eta. So you can think of that as like injecting xi into the scope and then evaluating eta with that new scope. So we can be formal about this, and you don't have to remember all that stuff. It's just maybe for benefit of you making connections. But what we'll do is define what we're going to do is define SID to be this piecewise function that either returns x. Yeah, so I've got a subscript and I've got two scripts going on because it's going to depend both on I and both on D. And D is going to be some element of our universe. And what it's going to do is return x if xi is not equal to x, and it's going to return d if xi is equal to x. Is that right? Right, sorry. This should be. So what we're kind of doing here is we're modifying the S bar that we're going to use, given that we know the value of one of the elements. So yeah, maybe I'll continue, and then it should be hopefully a bit clear about what's happening here. So what we're going to do is, given this definition, we're going to say that S bar of phi is going to be true if and only if for all D in our universe, we have SI D bar eta equals true. So it's a bit complicated, but hopefully the intuition should be clear. So what we want to have happen here is we want the truth value of phi to be true if and only if it's true for all of these etas. But the problem is we don't know the contents of eta. So to evaluate the truthhood of eta under each one of these possible elements in our domain, right? So xi can be anything in our domain. We have to modify the truth value, or the truth function that we're going to use on eta, to basically inject the value of d into the scope such that it'll return d if it ever encounters xi, right? Because xi is the variable that we're quantifying over, right? That's fixed. We fixed I. And then we're going into eta, and we're saying anytime you see xi, replace it with the value d. And we're going to do this for all possible d. And if it returns true under each one of these possible substitutions, then we're going to say it's true. Is that clear? The question you're asking arises from the fact that we've got both S and S bar, and the fact that S bar depends on S. And now we're changing our bar, but we're not saying anything about what's happening to the underlying S, I think. So yeah, this is admittedly a little confusing, but I think the way to kind of resolve that and to answer your question is that this modification is going to be happening to both S bar and S, I think. I think you have to do the same thing to this. No, do you? Wait, no, you shouldn't need to modify S because you never, this depends on S, right? But you only get into this case if xi is not equal to x. So I think it should be fine, yeah?
So might have been getting at what you were already talking about, but so in the case that xi equals x, that SID function returns d, but d is an element of the universe, whereas
Yeah.
you're comparing it later, the result of that function to true. So
Yeah.
how can it return d if it's supposed to return a true or false value?
Yeah. Yeah, so I think, this is a good question. And the reason it's okay is because when we're applying it to eta, the only places it's actually going to hit this case is when it's inside one of the atomic formulas. And then it's not like this whole thing is going to be returning D.
Oh, I see. That's kind of like a recursive definition that replaces all levels.
Yes.
Yeah.
It's from that weird thing where we had it either return true, false, or an element of the universe, depending on.
Yeah, I think I might need to do something to actually formally resolve that. I don't
Yeah,
think
like
I've
you have to
actually.
redefine all levels using the whole IAP thing.
Yeah. But yeah.
So
Yeah, it's good that we're able to think about this, but I think it's not too important for purposes of what we're doing here. We're kind of just trying to show the intuition of what's actually happening here. And the important concept here is that you're substituting in the value of D anywhere it occurs inside eta. Okay? So hopefully we don't have to use this sort of stuff too much. There are a couple theorems that do have to use it, but I think in the interest of time for the course and the fact that we've already kind of seen it when we covered propositional logic, we won't actually prove it. So the theorems are that any well-formed formula has a unique decomposition.
You still haven't covered the there exists case.
Oh, yeah, so the there exists case is going to be the exact same except for some, right? It's going to be the exact same construction, and then you're just trying to find some D in the universe that has it to be true. So that should be simple. So the one theorem we have is that any well-formed formula has a unique decomposition, and we saw this in the case of propositional logic. To prove it, you basically do the same stuff using the fact that we have IAP and these brackets that are basically eliminating the possibility of ambiguity. And as a corollary to this is that S bar is well defined, right? Because we only have one way we can inductively break down our formula, so we only have one path down this recursive tree that we can take. So we have a unique way of evaluating any well-formed formula. In other words, our S bar function is going to be well defined. And we don't need to prove all of that in the interest of time. It should be similar to what you've seen before. We want to move on to more interesting things. So I just want to go over maybe one quick example that tries to bring all of these things together to sort of solidify all of the concepts. So what we'll do is we'll define a language for graph theory. So what is this language going to look like? Well, what we're going to do is, again, looking at the syntax, what we want to do is have our constants be our vertices. Then what we're going to do is have no functions. And we'll just introduce two relations that allow us to play with this, R and P relations. And this is purely syntax, so I'm not yet actually saying what these R and P are going to correspond to. But is everyone familiar with theory, like graph theory? Yeah, I think you should have seen it already. Okay. Yeah, so a binary tree is a particular example of a graph that's acyclic. This is going to be slightly more general. So that's our syntax. And then our structure. In order to introduce our structure, we have to say what our universe is, what our vertices are going to be, and what our relations are going to do. So in effect, we have to actually provide a graph to come up with the relation. So an example would be maybe we have A, B, C, D, E, or so we just have a path from A, B, C, D back to B, and then E to F back to F. So this is our graph. And what we want to do is encode this graph in the semantics of our language. So our universe is going to be the same set as our constants. So our constants are going to fully span everything in our universe. It's not always going to be the case that we have one constant for everything in our universe. Like in natural numbers, we don't have a constant for every number. We don't have any functions. Then what we're going to do is encode the edges in R. So what we're going to do is say that our UV is going to be true if and only if UV is in AB, BC, CD, DB, EF, and FF. So this relation takes two parameters and returns true if and only if U is a directed edge to V. And then P will have encode all of the pairs of vertices that have some directed path between them. So I won't explicitly list all of it out, but we'll just say that PUV is going to be true if and only if U to V is connected by some directed path. Okay. And now what we can do is play with this a bit. So we can make sentences such as RUV implies PUV. So anytime there's an edge between two vertices, there must be a path between those two vertices. We can do less trivial things like for all U, for all V, if we have a path from U to V, but we don't have an edge from U to V. So this isn't the case where we have U and V and they're connected by some path, but not by an edge. So they don't have an edge. If this is the case, then there must exist some Z such that there's a path from U to Z, and there's a path from Z to V, and U is not Z, and V is not Z. right? So if they're connected by some path, then there must be some intermediate node Z such that U is connected to Z and Z is connected to V, but Z is neither U nor V. Okay? And maybe one interesting exercise might be to show that this fully defines P. So even if we weren't told a priori what PUV was going to be for all pairs, knowing that these two things have to be true for all UV, we can use these two tautologies to deduce what P must be. And that should be fairly intuitive because it's kind of a recursive argument going on here. If we ever have an edge directly between them two, then that's our base case. They must be connected. If they if they don't have an edge between them, we just try all possible intermediate nodes and recursively ask, is there a path from U to the intermediate node? Is there a path from that intermediate node to V? And then use that to define PUV. Okay? And we could, in theory, also argue that these two things are tautologies using our definition of S bar and using our choice of R and P. But we're not going to do that right here because our intuition suffices. I guess one last thing I wanted to point out was that, so I think this brings pretty much everything together except for we haven't yet involved the idea of free variables or S bar. So just as one last example, maybe what would S bar of PUU be equal to? Or rather, when is this statement going to be true? What conditions on S have to hold for S bar of PUU to be true? Yep.
Do you want me to express it like that? Because I can just say that there has to be another node such that there's a path from U to that node and from that node to U.
So I was thinking explicitly in terms of like, what does SU have to be? So like the only thing that the information that we're missing when we're trying to evaluate this truth statement is we don't know what S is, and we have a free variable, so we need to know what S is. So we can kind of turn this around and say, well, under what conditions on S is this going to be true, given our extension? So recall that S maps elements in our universe, S maps variables to elements in our universe, and then that gets extended to go inside of P. So this is only going to be true for the variables or the constants that have a loop or have a path back to themselves, right? So that's B, C, D, and F. So this is going to be true if and only if S maps U to one of those possible elements in our domain. In other words, these are the possible truth assignments that will, when extended to S bar, evaluate our well-formed formula to be true, because those are the ones that have some path from U back to themselves. Okay? that's all I had for today. Good luck on your midterm, and be sure to come to our office hours if you have any questions.